Hello, space enthusiasts and curious minds alike. Welcome back to our channel, where we dive deep into the mysteries of the universe and bring the cosmos closer to you. Today, we're embarking on an extraordinary journey, guided by the latest breakthrough from the James Webb Space Telescope. There are no more excuses. Yes, you heard that right. The Webb Telescope has found the first tangible evidence that's shaking up our understanding of cosmology. So, fasten your seatbelts as we explore this groundbreaking discovery together. Perched about 1,000,000 miles from Earth, the James Webb Space Telescope has taken breathtaking images of our cosmic neighborhood, simultaneously gazing back over 13 billion years to a time when the universe's earliest stars and galaxies were forming. As it probes the inaugural chapters of the universe's history, James Webb has stumbled upon intriguing pieces of evidence that challenge our existing cosmological models. These groundbreaking images from the early universe force us to reconsider long-held theories, posing a formidable challenge to the prevailing narrative of cosmic evolution. The question arises, does this call into question the standard model of physics? Join us as we explore how James Webb's insights into the ancient cosmos are revolutionizing our fundamental understanding of it. The universe's first billion years were pivotal for its development. In the immediate aftermath of the Big Bang, matter and light were intertwined in a scorching, dense mixture of elementary particles. But within a fraction of a second, the universe underwent a rapid expansion, cooling sufficiently to allow light and matter to separate. From the cosmic mixture, matter began to differentiate, leading to the formation of hydrogen atoms some 380,000 years after the Big Bang. These atoms created an intergalactic haze, plunging the universe into darkness due to the absence of light from stars and galaxies, a period now referred to as the Cosmic Dark Ages. It wasn't until several 100 million years post-Big Bang that the first stars and galaxies emerged, illuminating the universe with intense UV light. This light was powerful enough to ionize the hydrogen fog, transforming it into the clear, intricate, and stunning cosmos we observe today. This transformative era, known as the Epoch of Reionization, represents the first billion years of the universe's history when the hydrogen fog was being dispersed. To grasp this era fully, researchers delve into the origins of the first stars and galaxies, their characteristics, and their capacity to emit sufficient UV light to dissipate the hydrogen. A critical part of understanding the Epoch of Reionization involves identifying and verifying the distances to galaxies believed to have played a key role in this process. Since light travels at a set speed, it takes time to reach our telescopes, allowing astronomers to view celestial objects as they existed in the past. For instance, the light from the center of our Milky Way galaxy takes approximately 27,000 years to reach Earth. This means we observe the galaxy center as it existed 27,000 years ago. To witness the universe's initial moments after the Big Bang, we must look towards objects at extreme distances. Galaxies from these early epochs are so distant that they appear very faint and small through our telescopes, primarily emitting light in the infrared spectrum. This necessitates the use of powerful infrared telescopes like the James Webb Space Telescope to detect them. Before the Webb Telescope, the distant galaxies astronomers could identify were often the brightest and largest simply because our telescopes lacked the sensitivity to observe the fainter, smaller ones. Yet, it is these more numerous, less luminous galaxies that are believed to have played a crucial role in the reionization process, not the luminous giants. Studying these faint galaxies in greater detail is akin to understanding human evolution by examining entire populations instead of just a few exceptionally tall individuals. By enabling us to detect these dim galaxies, the Webb Telescope is providing a fresh perspective on the early universe, offering insights into the more representative drivers of cosmic evolution. In the nascent stages of the universe, galaxies bore little resemblance to the complex structures we observe today. Initially, these galaxies were predominantly composed of hydrogen and helium gas, embodying a state of primordial purity. Over millennia, the stars within these galaxies fused atoms together, creating heavier elements. The death of these stars in supernova explosions scattered these heavier elements throughout the galaxies, enriching them with the very materials necessary for life. These early galaxies had not yet evolved into the majestic spirals or the voluminous elliptical shapes familiar to us. Instead, they were smaller, more chaotic in structure, making their detection a challenge. The earliest galaxies discovered were about 1% the size of the Milky Way, yet they were in a phase of rapid growth, forming stars at an astonishing rate. Abundant fuel, in the form of cool hydrogen gas streams, flowed into these galaxies, drawn by gravitational forces. Frequent collisions and mergers between galaxies spurred on their growth and initiated new waves of star formation. As the universe continued to expand, the pace of galaxy growth decelerated. Significant mergers became rarer, and the once plentiful gas supply started to dwindle. This narrative forms the backbone of our current understanding of cosmic history, though it remains a work in progress. Numerous questions persist, especially regarding the details of these early stages, as we strive to piece together the universe's vast and intricate puzzle. As we delve into the universe's earliest epochs, numerous questions arise. When did the first galaxies emerge? How diminutive were they? And what forms did they take? Were they the building blocks of future galaxies, characterized by concentrated regions of star formation? Or were they fragmented and irregular? Did they exhibit uniform bursts of star formation? Or were some more placid, resembling contemporary galaxies? Did any early galaxies have the opportunity to organize into disk-like structures akin to the Milky Way? Or were they too frequently engaged in mergers? Will we ever encounter galaxies pristine with hydrogen and helium gas? Or did early supernovae swiftly enrich them with heavier elements? Additionally, how swiftly did these early galaxies accumulate mass and proliferate? And could they have played a pivotal role in reionizing the universe? With insights from the James Webb Space Telescope, we are edging closer to resolving these inquiries. Equipped with its infrared capabilities, James Webb is uncovering a plethora of distant galaxies beyond the reach of Hubble, offering unprecedented detail of the early universe. Its imagery acts as a tide, ushering in new waves of evidence and understanding. Recent research utilizing James Webb's data has revealed that dwarf galaxies in the early universe often exhibit a flattened morphology, elongated along a single axis. This new knowledge marks a significant stride forward in our comprehension of the cosmos's formative stages. Some galaxies in the early universe appear as slender oblate ovals, resembling surfboards, while others take on a more frisbee-like, flattened appearance. These galactic frisbees become increasingly prevalent as the universe ages, alongside the emergence of compact, spheroidal-shaped galaxies. Viraja Pandya, an astronomer from Columbia University and the lead author of a recent paper detailing this research, remarked in a press statement that roughly 50 to 80% of the galaxies analyzed exhibit flattening in 2 dimensions, indicating their common occurrence in the early universe. This finding is surprising, given their rarity in nearby galaxies. The discovery was facilitated by data from the CEERS, or Cosmic Evolution, Early Release Science Program, a component of the James Webb Space Telescope's mission aimed at uncovering the mysteries of the oldest and faintest galaxies in the cosmos. This era spans from 600 million years after the Big Bang to 6 billion years later, encapsulating the formation, evolution, and maturation of galaxies like those we observe today, ranging from spirals such as the Milky Way and Andromeda to massive ellipticals like Messier 887. The CEERS program builds upon previous research conducted by the Hubble Space Telescope, particularly in its exploration of the early universe through deep field images and the Cosmic Assembly Near-Infrared Deep Extragalactic Legacy Survey, CANDELS. In the Deep Extragalactic Legacy Survey program, the Hubble Space Telescope unveiled that massive galaxies in the early universe often exhibited a shape resembling oblate spheroids, akin to today's elliptical galaxies. Conversely, less massive and consequently fainter galaxies posed a challenge for Hubble's detection capabilities. However, among those it could discern, many displayed elongated forms, appearing as chains of brighter blobs or irregularly shaped dwarfs affectionately dubbed tadpoles, nuggets, or clumps. The question lingered, were these observations by Hubble a genuine representation of the shapes of smaller galaxies in their early stages? In essence, the answer is affirmative. The enhanced vision of the James Webb Space Telescope now confirms the validity of Hubble's earlier findings. Karthik A., also from Columbia University, elucidated how James Webb's superior vision and sensitivity are revolutionizing the study of early galaxies. The ability to identify additional categories of early galaxies is exhilarating, offering a wealth of new data to analyze. Consequently, researchers can delve deeper into understanding the relationship between galaxy shapes and their formation processes with unprecedented detail. As a result, a clearer picture emerges of how galaxies might have evolved and expanded throughout cosmic history, shedding light on the distribution of matter across the cosmos. The universe is primarily structured within a vast cosmic web of interconnected filaments stretching across space. These filaments consist mainly of dark matter, with a portion of regular matter mixed in to form the galaxies we observe. The prevalence of surfboard-shaped prolate galaxies can be attributed to their formation within halos of dark matter, which align with the cosmic web's filaments. As other dwarf galaxies form within these filaments, mergers occur along them, resulting in the elongated shape characteristic of prolate galaxies. Over billions of years, the cosmic web's filaments disperse and become more diffuse, leading to a reduction in merger rates and a decline in the proportion of prolate galaxies. As galaxies spin and evolve, they gradually adopt a more flattened, oblate structure. This transition is observed as the percentage of oblate galaxies increases from 20 to 60% over time, regardless of their mass. Similarly, spheroid galaxies become more prevalent as compact, star-forming galaxies settle down, eventually becoming the precursors to the massive elliptical galaxies we see today, or the spheroidal bulges of large spiral galaxies. Understanding the evolutionary trajectory of galaxies throughout cosmic history is crucial for unraveling the complexities of the universe's development. The James Webb Space Telescope has a primary goal of advancing our understanding of the cosmos. Recent discoveries from the CEERS program suggest that hierarchical mergers, where smaller galaxies merge with larger ones along cosmic filaments, play a crucial role in shaping the diverse structures of galaxies. Alongside its remarkable imagery, the Webb Telescope has unveiled perplexing phenomena previously unseen by other telescopes. For instance, it has identified several galaxies in the early universe that defy expectations, boasting masses ranging from 10 billion to 100 billion times that of our Sun. These colossal galaxies challenge the predictions of the standard model of cosmology, also known as the lambda cold dark matter model. This discrepancy highlights a significant unresolved issue regarding the properties of galaxies derived from observational data. Michael Bone-Colchin, a cosmologist at the University of Texas at Austin, remarked on the surprising nature of these findings, describing the period following the release of the initial data as an exciting and unprecedented flurry of activity. The images captured by the Webb Telescope have sparked a wave of exploration and analysis, reshaping our understanding of the universe's early epochs. The images captured by the James Webb Space Telescope are undeniably breathtaking from an aesthetic standpoint. However, scientists like Bone-Colchin have uncovered numerous enigmas within the telescope's observations, including the puzzling existence of massive galaxies appearing approximately 500 million years after the Big Bang. These galaxies, dubbed early behemoths, pose a significant conundrum as their immense size suggests a rapid growth rate that defies conventional expectations. Webb's observations hint at a potential explanation tied to the rapid expansion of supermassive black holes during this era. Nearly all modern galaxies, including the Milky Way, harbor supermassive black holes at their cores, indicating a fundamental aspect of large galactic structures. If black holes in the early universe underwent rapid mass accumulation, it could account for the abundance of massive galaxies seen in the telescope's images. However, this proposed explanation merely swaps one mystery for another, as Bone Colchin elucidated. If it indeed transpires that massive black holes contribute to the inflated appearance of these galaxies, it introduces a new layer of complexity to our understanding of cosmic evolution. This revelation underscores the ongoing quest to unravel the intricate workings of the universe and its enigmatic phenomena. There are perplexing puzzles surrounding the rapid growth of massive black holes in the early universe. One conceivable explanation is that an unknown mechanism in the early cosmos accelerated the process of star formation, resulting in the seemingly massive and luminous appearance of these early galaxies. Another intriguing possibility is that these galaxies harbor a population of stars known as population III, the first stars ever to illuminate the universe. Detecting these stellar ancestors has long been a goal in astronomy, but their extreme distance in both time and space poses significant challenges. Population II stars are anticipated to be brighter and more massive than their descendants, suggesting they could be concealed within the distant galaxies observed by James Webb. However, if none of these hypotheses prove satisfactory, it may be necessary to entertain the notion that these ancient galaxies have exposed a fundamental gap in our understanding of the universe. Perhaps the observations made by James Webb indicate that our current standard model, the lambda cold dark matter model, is incomplete, hinting at the presence of a missing component. There are indications that this may indeed be the case, urging us to reconsider and refine our understanding of the cosmos. The discrepancy between calculations of the universe's expansion rate based on early cosmic epochs and direct measurements in the local universe poses a puzzling challenge known as the Hubble tension. Some proposed solutions to this disparity involve introducing additional dark energy at very early times, just 50,000 years after the Big Bang. Interestingly, these early dark energy models predict a faster evolution of structure and a greater abundance of structure at high redshift, aligning with observations of massive early galaxies. It's intriguing that a single solution could potentially resolve both of these observational discrepancies. Clearly, scientists have their work cut out for them in deciphering the true significance of these perplexing images. Future observations will play a crucial role in confirming whether these galaxies truly possess such extraordinary mass. Astronomers also intend to survey larger patches of the sky to ensure that these findings aren't confined to a single region. However, for now, we must grapple with the unsettling presence of these colossal galactic giants at the boundaries of space and time. Recently, astronomers using the Hubble Space Telescope made a groundbreaking discovery. They found that the atmosphere of a relatively small planet outside our solar system is abundant with water vapor. However, before you start planning a vacation to this distant world, it's important to note that the planet's surface is scorching hot, reaching temperatures high enough to melt lead. This renders it inhospitable to life as we understand it. Specifically, the exoplanet known as GJ 9827d exhibits temperatures akin to those found on Venus, reaching a sweltering 752 F or 400 C. Nevertheless, this discovery remains remarkable. While scientists have detected water vapor in the atmospheres of numerous extrasolar planets previously, the observations from the Hubble telescope offer a unique perspective on this hot and humid world. GJ 9827d represents the smallest exoplanet to date where water, a crucial element for life, has been detected. Laura Creedberg, a team member and director of the Atmospheric Physics of Exoplanets Department at the Max Planck Institute for Astronomy, expressed excitement about the discovery, highlighting its significance in expanding our understanding of planetary systems beyond our own. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blisovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blisovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.